Yeah, hello and welcome again to another episode of AVL's Launch and Learn Summer Series. This year we cover advanced air mobility. My name is Thomas Glatz. I'm Senior Technical Specialist here at AVL in North America. And almost a tradition by now, every week in August, we cover an interesting simulation topic live on LinkedIn. The recording also will be available on YouTube later on. And you can interact with us and our speakers directly through the chat function on LinkedIn. This week's topic is about hybrid electric aviation, how we can extend the range of our aircrafts and enabling new missions. And with me is my colleague, Heather Baroody. Heather, welcome.
Hi, thanks for having me.
And yeah, I'd say we jump straight into the topic. When we look into an battery electric aircraft, we put here some numbers on the screen. Did some simulations on a mission range study here with an aircraft with approximately 3,000 kilogram, with the assumption of having 1,000 kilogram on the battery, about a third of the aircraft mass. We can achieve a 30-minute mission with 250 kilowatt installed, 160 kilowatt usable to have some spare range for emergencies available. And truly the battery limits the range of the aircraft, of the electric aircraft, and also the battery mass limits how much energy obviously we have available to achieve our mission duration, but also range. So now what would happen if we wanted to increase the range? One might say simply, okay, we add more batteries. If we look at this case study, what happens if we increase the battery amount in the aircraft without changing too much else, keeping the architecture intact? If we hypothetically add 400 kilograms of additional battery, about 40% more battery mass, we can increase the flight duration by 45 minutes. But you might be able to spot the big drawback or caveat here. We only would be having 100 kilograms of payload left, and that's basically the weight of the pilot. We have no room for cargo or passengers, so obviously this is not going to work very well in practice. So what if we use a hybrid instead to increase our range? If we look at such a scenario, comparing again, let's assume we shrink the battery down to 200 kilograms. We instead use a range extender, for example, and obviously fuel for that range extender, which might approximately have a mass of 500 kilograms. It still leaves us 500 kilograms for payload, same as the original battery electric aircraft. But this combination would be able to achieve us a 200 minutes of mission. So about 7 times more mission time with the same payload, with the same aircraft, basically with the only drawback of adding more complexity on the powertrain system. Yeah, it will be a more complex system, maybe a more costly development, more parts, for example, but at the same time, this increased capability might benefit you. So how can we achieve the different powertrain or hybridization concept? I mean, starting with the all-electric aircraft, we see a little bit of a schematic that we obviously at the center of the aircraft, we would have the energy storage system, aka the battery in non-aviation terms. And the battery powers, the ESS powers the e-motor. E-motor goes mechanically, the green line, to a propeller shaft, and the propeller or fan, however you want to call it, also powers consumers on board. Now, if we would like to extend the system and achieve a hybrid configuration, we have a bunch of different options. So the ICE-based option, or one of the options, might be that we add simply an engine and an electric motor both of them mechanically connected to the shaft, can be mixed or through a gearbox, basically, but both can power, if it's a true hybrid, both can power the propeller independently. Now we could also switch to a series hybrid. So the previous one was a parallel hybrid, so both can actually power the aircraft. Now with the series hybrid, only the electric motor will power the propeller or the fans in the end. So, and we have different variants also how we could achieve this here. So one example would be here a fuel cell system that generates the necessary energy, stores it in the energy storage system, the battery, and then the electric system is basically mechanically disconnected from the e-motor or from the propeller, just powers electrically the e-motor, and the system operates in that kind of way. One might also think of, depending on the size of the energy storage system, okay, this is kind of like a range extender. So the fuel cell system extends the range of the battery, which might be rather small or could be also potentially on the larger side. So depending on what the use case is. And this can also be achieved with an internal combustion engine or a conventional combustion engine, a turbine potentially as well, and where the ICE acts as a range extender. And so this is then paired with since the ICE, not like a fuel cell would create electric power out of the box, it needs to be paired with the generator. The generator is creating the electricity that's stored in the battery, and then this is powering the electric motors. But this is not the end of the story. So there are even more potential variants. So there could be mixed variants where it's a mixed style hybrid where we would have electric powered propellers, but also we might have a main propeller, for example, that's always ice powered, or and that also powers the generator. So here's a kind of like a layout for such a mixed system. And it even becomes more complex when we move on from a pure or from an aircraft, conventional aircraft, to eVTOL applications, drone applications, advanced air mobility, so to say, where we not only can consider basically one dimension, but we might have also the vertical takeoff aspect of it. And again, this multiplies really the potential variants. So we could really look at coupled and decoupled systems. So coupled, basically everything depends on one energy, the storage system, or decoupled, where, for example, the vertical propeller or takeoff e-motors are powered here, in this case, for example, by the battery, and the horizontal propulsion is powered by, for example, a conventional ICE device, let's say it like this. Yeah, and similar, we could do parallel hybrid architectures, and again, vertical and horizontal, for example. And one can already imagine that the number of potential useful designs multiply. So that's really a challenging engineering problem, a nice engineering problem to have, and a very nice engineering problem to solve with the help of simulation. And yeah, to tackle this, what we are doing mainly at that stage of the development is we set up a system simulation model. You see here on the left side a bit of a sketch how we would model the architecture. So in this case, it's a cargo drone that we modeled here, a quadcopter layout. And yeah, to give you an example of such an architecture. We have to consider the different physical domains. So we see in orange here the electric network. We see control functions on the around here, because we obviously would need the control functions, and also it's quite important to have a proper mission definition of flight route included here. And this allows us then to run studies like this, as you see it here, that we would have a flight profile based off altitude and velocity, and the aircraft would simulate this flight route accordingly, and we see live trade-offs here of energy flows and power flows, as well also of the thermal aspects of the aircraft. Because especially with hybridization and the electrification, the components are highly dependent on temperature. So the battery, especially the battery's power and capabilities, is highly dependent on the on the temperature. Same goes for fuel cells. Need very defined, let's say, temperature conditions, and also efficiencies of e-motors and other power electronics components would depend on temperature as well. So even for such a simple, let's say, layout compared to some of the more complex hybrid powertrains we saw earlier, this multi-domain aspect is very important, and therefore we typically run even these simple systems always as a multi-domain type of simulation. Now, to give you an example, because specifically today we speak about hybrids, if we extend now this model with an internal combustion engine and the generator, you would see it here on the sketch here, which obviously makes the operation of the aircraft much more interesting, as we now need to balance and want to balance when is the ice kicking in, when is the battery empty, when it is charging again, and how is the thermal management system behaving here. And the simulation now allows us also, again, live during the run or also afterwards, to analyze the different energy conversions within the system, and on the long run then optimize the operating strategy of the entire hybrid system here. But to give you a real, like, let's say, practical insight, much better than the slides I showed here, Heather has prepared an actual example of a fuel cell electric aircraft, and I would hand over the screen to you. And
yeah, so now I've jumped into cruise here with the very similar structure, and we're looking at, again, the fuel cell and battery hybrid. So jumping quick, we can define our airplane here, and we have our pilot that we put all our inputs for how they're controlling the aircraft. And again, we can define different flight profiles that show what the inputs are, but more interesting, we have our system here. So again, we have the fuel cell, the battery, and this one is showing the series combination with the propeller and the e-motor. We can jump here into the fuel cell, and this is our stack model here, where we can define the different geometries of the stack, how many cells you have, and you really can dive into down to the specifics of different specific catalyst layer materials and gas diffusion materials, and really go deep there. Oops. We can look on, this is the anode side here, where we have our hydrogen, and here we see our water separator. So we have a water tank that pulls out the water to dehumidify it. And we can jump over to even the cathode side. That this cathode side is showing our air intake and humidification system with all the different pipes. And then looking even deeper, we have in this pink section the thermal management system here. So this is your coolant with different heat exchangers. And so you really can see that you can go quite into detail about which systems you want to add. And even so, we can go jump to and run a simulation. And with all that, it does run quite quickly. Once it starts, we can see it's faster than real time. We can see different gauge instruments, and this can all be, of course, catered to what you're interested in focusing on the engineering, your specific engineering question. So I can just stop it and we can jump to the results tab. And we can see different different metrics that you're interested in. And the energy flow diagram we can pull up all our results are over here, any metric you want to see. But the energy flow diagram is pretty cool to see. So I think it's worth pulling up. You can really it's just as easy as dragging and dropping. And you can click what you want to see. We can play, and it'll play the different diagrams. I mean, I only ran it for a pretty short amount of time, so there's this, and we can see power. Yeah, so was quite a quick crash course on the fuel cell, but you can see that you really can dive into any amount of detail, expand it, add humidifiers, and throw in the chat any questions, but I can give the screen back to Thomas.
Yeah, maybe just stay a bit here because I think it's quite impressive how detailed actually you can go on the component level while still being real-time capable, or even faster. I would say at some point it's almost like the system model here turns it, maybe if you even detail the fuel cell model a little bit more, turns into a fuel cell model with an aircraft around it. Let's say if you're, for example, even more interested in certain degradation aspects of the fuel cell, or same could be done for the battery if the battery is more in the focus. Yeah, these types of models really give you a lot of flexibility. And I mean, Heather, you showed today the kind of like the single calculation run or the live run. But obviously, one other option to operate these models is then to compare different variants, different parameters in an automatized way, and you would run typically many simulations in parallel, depending on your computational power. A workstation maybe something like 100 simulation models at a time or overnight, and yeah, really. Can compare all different kind of sizing options, maybe also different flight profiles, different use cases, so you can get really a good understanding if the design that you're developing will achieve the necessary targets. Yeah, thanks a lot for sharing the live demo with us. I will maybe just go back into the presentation, and maybe the question might arise why we even looked at the fuel cell. It has a good amount of advantages. The hydrogen as a fuel, besides if it's produced carbon neutral with an electrolyzer, for example, if it's liquefied, has a high energy density. Most recent studies, I would say, show that the liquefied hydrogen shows better energy density and range on hybrids than conventional fuel. We have high power density of a PEM fuel cell. We have low vibration because there's basically no explosions or rotating parts in there besides a compressor, for example. There's also downsides, and the simulation model is really helping explore and avoid these downsides as good as possible. So start-stop time is one of them. Fuel cell doesn't like to be operated in too much transients. It's like stationary loads. It also operates more efficiently under lower loads, further away from peak power. There is some robustness topics, and also degradation, especially if it's operated very transiently, is a challenging aspect. We have very good degradation models available specifically for PEM fuel cells that allow you to investigate the trade-offs. So this can be, and Heather is actually an expert in those and can for sure share more if there are questions about it. But there is membrane degradation models we are working on, catalyst models. So really still a lot of research also going on that aspect. And just moving on. Yeah, so some of the use cases you would see then in the end. So you would use such a model potentially for compressor sizing, for sizing of balance of plant components. As I mentioned also, to develop the control strategy of the entire system in the end, so of the subsystem, but also then the broader system where thermal management would be included, which obviously is very important for the range. And looking even deeper into the component development, today we've been on the system level side for the majority of the time, so we can go maybe to a very coarse 3D in AVL Cruise-M that Heather showed. But if it needs to go deeper, we also would look into 3D CFD simulations. So here you see a couple of images that were done in AVL Fire-M on fuel cell designs. And here it would really go into the depth of the component development and, for example, the channel layout, the exact channel layout, flow patterns in that in the cooling channels and the bipolar plates as well. The supply and pressure losses of cooling fluid, but also the media supply here, and also the detailed thermal management of the stack. Yep. Besides fuel cells, obviously there's also other interesting applications. So rotary engines are quite interesting for the drone applications, certainly VTOLs potentially as well, because they're quite compact. They're also very smooth running in terms of vibrations, and quiet also. So if an aircraft needs to hover and stay long in the air and circle, this is quite an interesting concept. On the downside, the efficiency overall is not that great. So hybridization is really key for a rotary engine as well. There might be some sealing issues, or it's a challenge, let's say like that. And then also the lifetime of the engine might be a con, but maybe not for every application as important. Yeah, the rotary engine, we've have a long history of simulating it, but also recently it's fully available again in, let's say, our modern simulation technology. So in AVL Cruise M and Fire M, the M series that Heather demonstrated, and also the coupling of 3D CFD and the 0D1D system simulation is a big simulation topic for us here. Yeah, here you just see one quick case study or example where we would pair the two different simulation domains. And yeah, we would simulate in more detail the rotary engine and then use simulation results, for example, directly combustion profile, as you see here, for the rate of heat release in our Cruise M system simulation model. And yeah, we can route back different intake or exhaust conditions to the 3D and kind of like run this in a paired loop, iterative loop, let's say it like this. And yeah, also in terms of vibrations and lubrication, we can look at this. So AVL Excite is a very good tool to investigate any NVH and durability topics. And I think, yeah, that brings me to the pretty much right in time to the end of today's session. I hope you received a nice overview of some of the challenges of hybridization and also some of the simulation capabilities that would help you tackle this. Yeah, battery electric, pure battery electric clearly might show some mission limitations, but there are good hybrid approaches out there that can help. And I think simulation can help a lot of dealing with the additional complexities of such a hybrid system. Yeah, I think that only leaves me with an outlook on next week's episode. Heather will be back actually and will bring a new guest. So I think we will deal with digital twins and the route simulation for electric aircraft operations. And yeah, hopefully you will be joining again next week. And that leaves me with a thank you from my end. I will head into summer vacation and wish you a pleasant end of the series for this year. Thanks a lot for joining and bye-bye.